Okay, so for the bell ringer, we have 2 people pushing a car versus 3 people pushing a car. With the 2 people, you notice that their input force is 2 newtons, where the force of friction is 2 newtons. That is a balanced force. I saw a couple people tell me that this was unbalanced, but nobody told me that this was balanced. But yes, this is a balanced force. Whereas if 3 people pushed, that is a unbalanced force because now they're pushing with 3 newtons of force, while the friction of the car is 2 newtons. So what we could say about the first one is that if 2 people push the car, it is a balanced force, and the car will not accelerate. It will travel at a constant speed. In the bell ringer here, it already said it's moving at 2 meters per second. So with the 2 people pushing, I would expect it to continue to move at 2 meters per second. Whereas with 3 people pushing, I'm going to expect it to accelerate. Okay, so with 3 people pushing, it is an unbalanced force, and the car will accelerate to the right with a net force of 1 newton. So it's not going to stay at constant speed, it's going to accelerate. With that being said, again, you get a grade for these bell ringers. They add up at the end, so make sure that you're getting the bell ringer done. I only see a few of them in there. Okay, so today, everybody get out your science spiral. We're going to take some notes on speed. So everybody get out your science notebook. Guys, Lucas, Daniel, everybody science spirals. Everybody needs a science spiral. We're going to take some notes. The important thing we're going to do is near the end of the notes, we're actually going to be working some speed problems. And you need to do this because practice makes perfect. If you don't practice, you're not going to understand it when it comes time to you actually having to do it. All right, so the first definition is position. Position describes the location of an object to a reference point. Okay, so for example, if I was to describe the position of your house, I could say that your house is located behind the mailbox. That would be the position of your house. All right, but then we need to define a reference point. A reference point is what frame of reference are you using to describe your house? So we could say that your house is located behind the mailbox. We could say that your house is located on the street. We could say that your house is located in Texas, or we could say that your house is located in the solar system on Earth. So oftentimes, when we describe motion, we have to use a reference point. What reference point are we looking at? All right, so how fast are we traveling right now? I guess that needs to be a couple question marks. So how fast are we traveling right now? So if I asked you, you're sitting in your desk, are you moving? Are you moving while you're sitting in your desk? What do y'all think? Okay, and I'll tell you the answer to that all depends on the reference point, the frame of reference that you use to define motion.
Upon further reflection, you realize... How fast are you moving right now? That seems like an easy question. The first tempting answer is, I'm not moving. Upon further reflection, you realize that maybe the Earth's motion counts. So a second tempting answer is 19 miles per second around the sun. But then you recall learning that the sun moves around the center of the Milky Way galaxy. And the Milky Way moves within the local group of galaxies. And the local group moves within the Virgo cluster. And the Virgo cluster moves within... How fast are you moving is not an easy question. When mission control tells astronauts how fast they're going, there is always an assumed standard of rest. At the start of the voyage, speeds are given relative to the launch pad. But later, when the launch pad is just one more arbitrary place down there on Earth's spinning surface, speeds are given relative to the idealized, non-spinning, pinpoint center of Earth. On their way to the moon, Apollo astronauts had a hard time answering the question, how fast are you moving? Speed away from Earth was one thing, and speed toward the moon was quite another. That's because the Earth and the moon move relative to one another. Of course, speed is a relative quantity. When Captain Kirk asks Lieutenant Sulu if the Starship Enterprise has reached a speed of warp 7, Sulu should reply, relative to what, Captain? Such a sassy reply may get subordinate Starfleet officers in trouble, but it is the only good answer to the question, how fast are you moving? This is basic relativity talking. Not fancy Einsteinian relativity, but good old-fashioned and still correct Galilean relativity. Galileo seems to have been the first person to realize that there is no such thing as an absolute speed. Speeds are relative. This means that speeds only have meaning when they are referred to a reference frame. Presumably, that reference frame is itself at rest. But then we have to ask again, at rest relative to what? Because even the concept of rest has lost any hint of absolute meaning. Speed is relative and rest is relative. Earth's speed is 19 miles per second relative to the sun. The Enterprise's speed is warp 7 relative to the center of the Milky Way galaxy. Your speed is 0 relative to your easy chair. But depending on where you sit, it is hundreds of miles per hour relative to Earth's center. When we furrow a brow and ask, but how fast is Earth really moving? We imagine spaceship Earth plowing through the ocean of space as it orbits the sun. But space is not an ocean. It has no substance as water does. Space is not a thing. Space is nothing. Space is no thing. You can move between 2 points in space, say between Earth and Mars, but you can't move through space. There's nothing to move through. It's like trying to say how much a hole weighs. A hole weighs exactly nothing, because a hole is nothing. It's a void, and so is space. To move relative to nothing is meaningless. The concepts of speed and of rest have only relative meaning. They are absolutely meaningless. They mean something only with respect to arbitrarily chosen, artificial frames of reference. If someday you are buckled into your spaceship and you see from the side window, say, a space station whiz by at constant speed, there is no way to know which of you is really moving. Neither of you is really moving because there is no deep reality about constant speed. Constant speed in a straight line has only relative meaning, a kind of relative reality. Does this mean that all motion is relative? No. Some motions have only relative meaning, but some motions have absolute meaning, are absolutely real. For example, constant speed is relative, but change in speed is absolute. Calling something absolute in science means that arbitrary standards are not used in its measurement. It is unambiguously measurable. When your spaceship fires its engines, your change in speed is beyond doubt. You feel it in your stomach, and your ship's sensors can measure it. Outside your window, the passing space station may seem to be changing speed, but the beings inside the station will not feel it, and no sensors can measure it. You are really changing speed, and they really are not. There's something absolutely real about changes in speed. The same goes for rotation. If your spaceship is spinning, you can feel it, and your ship's sensors can measure it. The space station outside may seem to be going around you, but it is you who feels queasy, not the folks in the space station. You are really spinning, and they really are not. There's something absolutely real about rotation. So some motions are relative, and some are not. There is no deep reality about constant speed, but changes in speed are deeply real, and so are rotations. We have to be thoughtful in our analysis of everyday experience in order to identify what is deeply real. Since we can be fooled by perceptions as basic as speed, maybe every perception deserves careful scrutiny. This is what inspired Einstein to his incredible insights about the speed of light and forward time travel. Knowing how to identify what is deeply real is tough and important work. If a police officer ever pulls you over for speeding and asks, "Do you know how fast you were going?" an insightful, though perhaps unwise, reply would be, "Relative to what?" And then, as you sit in the back seat of the police car and feel it accelerate toward jail, you can add, "But some things are absolute."
Okay, so are you moving? It depends on what reference point you look at. After spring break, we'll get into Earth and space, actually into space science. And we start studying space. There's a video we watch of how the Earth travels through space. I've been studying science for a long time until I saw that video a couple years ago. It completely changed the way I look about our position in the universe when you look at how Earth actually travels through space. We're doing a lot more than just going around the sun. Okay, motion is a change in position over time. All right, next one is displacement. Displacement is how far an object is from where it began. So this is one y'all need to really take some notes on. I'm going to give you a couple example problems because you'll be working on these later. Let me see here. Try and get my train of thought. Okay, so everybody needs to be writing this down. Let's do some practice problems with displacement and distance. So the first thing, if I travel, let's say 10 meters, and then I stop, and I travel, well, let's say another 5 meters. Okay, everybody needs to be drawing this. Go ahead and draw it. So if I travel 10 meters, and then I stop, and I travel another 5 meters, question is, how far did I travel? What is my distance? All right, so first let's go ahead and put an X right there. And what would that X be? That would be your reference point. That's your reference point. So we're asking, how far did you travel from your reference point? Okay, well, 10 meters plus 5 meters gives me 15 meters, right? That would be my distance. Here. Okay, so my distance would be equal to 15 meters. That is how far I traveled total. But we also have a concept called displacement, and it's how far you are from where you started. Well, I am 15 meters from where I started. Simple enough. I'm going to give you all a couple seconds. Everybody needs to draw that and write that down. Okay, so the next set, let's do another example. So this time, I'm going to travel, let's say 20 meters this way. Then I turn around and I travel back, let's call it 17 meters. So the question is, what is my total distance? And then what is my displacement? Your displacement is how far are you from your reference point. Okay? So, this one here, my distance, the total distance I traveled is 20 plus 17, which would be 37 meters. Oops, 37 meters. So the total distance that I traveled is 37 meters. However, the question is, how far am I from where I started? So how far am I from where I started? What is my displacement? Because displacement is how far are you from where you started? Okay, well, if I travel 20 meters, and I turn around and I walk back 17 meters, how far am I from where I started? 3 meters, right? Because if I travel 3 more meters, I would be back where I started. So my displacement is equal to 3 meters. All right. If anything, for those of y'all who are hesitating to take notes, because you will be doing this later in this week, I would definitely at least write down this one right here. Your displacement is how far you are from where you started. Okay, whereas your distance is the total distance that you traveled. All right, everybody have that down?
Sir, can you keep it up there for a little bit longer, please?
Yes, I will wait. Okay, are we ready? All right, so moving on. Okay, so the next one is speed. Speed is how far an object has moved over a given amount of time. Everybody needs to write down this formula. Speed is equal to distance divided by time. So speed is equal to distance divided by time. And the unit for speed is the meter per second, or we could use kilometers per hour. Just to let you know, though, when you get to high school, they only use meters per second because it's the unit that translates to calculations such as power and work and all types of other things you'll be doing. All right. So if you remember density is equal to mass divided by volume. Well, this is basically the unit for speed. Speed is equal to distance divided by time, or meters divided by seconds. The best way to get these things correct is to always show all of your work. All right. Then we have instantaneous speed. Instantaneous speed is a given point in time. It's how fast you're traveling at a given point in time. That would be your instantaneous speed. So instantaneous speed, how fast you're traveling at a given point in time. When you get a speeding ticket, you're getting a ticket for what you're doing at that point in time. Versus an average speed. An average speed is speed over a period of time. So for example, this graph here, they traveled 1,200 meters in 80 seconds. Okay, so if I take 1,200, my distance, and divide it by my time, 80 seconds, 1,200 divided by 80 would give me my average speed. However, that would not be their instantaneous speed. For example, looking at this graph, this object went fast and then stopped, went fast and then slow. Okay, their average speed would be the speed over the entire trip. Their instantaneous speed would be some point along this graph. Like right here, they're not moving. Right here, they're moving fast. Right here, they're moving slow. If I point it to one point on that graph, that would be their average speed. So the question is, let's say I drive to Austin and the speed limit is 65 miles per hour. Let's say my average speed going to Austin is 60 miles per hour. Could I get a speeding ticket? And the answer is yes. Okay? Because on my way to Austin, let's say I drive 55 miles per hour, and then I get to a car that's blocking the road, or a car that's driving slow, and I go around them. I go around them at 80 miles per hour, and after I get past them, I slow down back to 55 miles per hour. Well, if I get caught doing that 80 miles per hour for that minute or two that I go around the other car, I could very well get a speeding ticket, even though my average speed, the speed from San Antonio to Austin, is lower than the speed limit. Okay, so instantaneous speed, when you get a speeding ticket, you're getting a ticket for what you're doing that second in time. Whereas your average speed is over the duration of the trip. You might go fast, you might go slow, you might stop. Okay, then we have velocity. A velocity is a speed with a direction. It is a vector. It has a size and it has a direction. An example of velocity would be 5 meters per second north or 25 meters per second down. Okay? If you have a speed with a direction, you have a velocity. And a vector is anything that has a size and a direction. Okay, then we have acceleration. Acceleration is a change in speed or direction. So if you accelerate, you change your speed or you change your direction. And y'all remember we watched that video. Is that an R? Is that an R you just made? I think it's sign language for R. Yeah. Make it very quick, so we're about to do some practice problems. Okay, if you remember that video of the airplane pilots in that centrifuge who were passing out, remember they were traveling at the same speed, but they were constantly changing their direction, so they were accelerating. So if you speed up, slow down, or change your direction, you are accelerating. Why? Because the definition of acceleration is a change in velocity, and velocity includes speed and direction. Okay, number one, If a ball travels 50 meters per second in 5 seconds, how fast is a ball traveling? All right, let's do some practice problems. I want everybody to write this in their science spiral because practice makes perfect. Get my Jamboard open. Okay, let's do some practice. Number one, if a ball travels 50 meters in 5 seconds, how fast is the ball traveling? First thing you need to do is write your formula. So let's go ahead and write it. Actually, you know what? First, let me move this out of the way, get this up higher. Here we go. What color? Green? All right, green. So, first thing we do is we always write our formula. Speed is equal to distance divided by time. For the first one here, let's go ahead and write our units. Meters divided by seconds is equal to, okay, how far did the ball travel? It traveled 50 meters. How long did that take? That took 5 seconds. What is 50 divided by 5?
10.
Very good. 10 meters per second. Okay? So the 3 steps here, just like when you solve density, first I write my formula, then I put in my units, then I solve. I call it plug and chug. You plug in your numbers and then you put it through the calculator. Which, by the way, for the next month, everybody needs a calculator. Actually, not that long. We're going to be doing these for the next month, but a lot of them are just, we'll be looking at graphs. But yes, we do need calculators. All right, so that's number one. Everybody got it down? Okay, second problem. Start off by writing your formula. Speed is equal to distance divided by time. Always write your formula first. My distance is 100 meters. My time is 3 seconds. What is 100 divided by 3? 33.3 meters per second. 33.3 meters per second. Okay, so again, my 3 steps. I write my formula, I plug in my numbers, and I solve. On the assignment we're going to do yesterday. On the assignment we're going to do tomorrow, if I don't see your formula, your numbers, your answer, you don't make a 100. Practice makes perfect, and this is all about practice. Number 3. A jet travels 7,500 meters in 30 seconds. How fast is a jet traveling? Write your formula. Speed is equal to distance divided by time is equal to, what's my distance? 7,500 divided by 30. What is 7,500 divided by 30?
250 meters per second.
Very good. And did I do this on the last two? I hope not. I'm not being a very good model. I forgot my units. 7,500 meters, 30 seconds. And yes, it is 250 meters per second. That's pretty fast. That's about the speed of sound. So again, my 3 steps. If I want an A, I write my formula, I plug in my numbers, I chug it through the calculator. Right there, I just made an A. You don't do that, no A for you. Okay? That's actually going to be it for today. We had some practice problems. We're going to do them tomorrow before we start tomorrow's assignment. That's it. We're in the last, actually tomorrow is probably the last day I'm going to take any late work. I'm going to sit down tomorrow and work my way through my grade book and work on finalizing grades. So if you have not turned in your, if you have any missing work, I should say, it is due by tomorrow, just as a warning. Okay? Stephanie, are you there?